Project 3.1.1 CHUMP Clock, Counter, and Code. CHUMP is a 5-stage project aimed at producing a 4-bit processor. The acronym CHUMP stands for Cheap, Homebrew, Understandable Minimal Processor. The objective of this stage is to create a clock signal for the rest of the 4-bit processor and a 4-bit signal to drive the rest of the operating devices. Additionally, a program is to be created in this stage to be implemented in the next. The clock signal is created by either one of two of the 555 timers. They are in order from left to right: astable, monostable, and bistable, which is used to select between astable and monostable. The astable clock is a familiar concept from the first project of last year, Project 2.1. The only significant difference is the new compound resistance of R2, which now includes a 100,000 ohm potentiometer. The new monostable clock in the middle is essentially a button debouncer using a PBNO plunger. Essentially, it verifies the status of the PBNO plunger with 3 degrees of certainty to produce an output with the trigger comparator. When the voltage is higher from the negative input lead, which by default it is, it produces a low output through the 3 inversions. When it is higher on the positive lead, when the button is pressed and grounds the trigger, the output is again inverted 3 times to produce a high instead. The bistable clock is essentially a switch debouncer for an SPDT switch with the center lead grounded and the side leads pulled up. If the switch is grounding the trigger and holding reset high, the output pin yields a high. The high reset signal is an extra precaution to certify this reading. The opposite would occur if the reset pin were low and the trigger were high, the output would be low. These 3 clock signals feed into a combinational NAND circuit. The diagram here is color-coded so that the green line comes from the monostable clock, the yellow line comes from the astable clock, and the black line comes from the bistable clock. This diagram is a better demonstration as to what the combinational logic circuit is able to do. It has 3 different scenarios, one labeled in green, one labeled in purple, and one labeled in blue, and it also has a halt line which is incorporated later within the CHUMP project. When the bistable clock outputs a high, which is the green situation in this diagram, the output of the combinational circuit is the astable pulse. If the bistable clock output is a low, then the combinational circuit yields the monostable pulse, which is the purple scenario here. The output is 0 if the halt line is held high, regardless of what the status of the bistable switch is. In this stage, it is currently grounded to prevent this from happening. With the clock pulse now installed, the first parts of CHUMP can be built. These parts are highlighted in the green box. The purple arrows lead to areas where the clock pulse is used. The last component of this stage is the program counter, which converts the clock pulse into a 4-bit signal and can also take in 4-bit inputs to create a 4-bit signal, which is used to call on an instruction in EEPROM, which is added in the next stage of this project. The program counter is very similar to the 4516 IC that was used in the counting circuit project. The only difference is that it's made for more accurate use with its data input pins and clock carryout so that it can be used with multiple other program counters to create another 4-bit pulse or stack 4-bit pulses to create an 8 or higher bit pulse. What the program counter is meant to do is turn the clock pulse into a 4-bit pulse, which can be used by the rest of the CHUMP as it reads in 4 bits. This is what it does when load pin, or pin 9, is wired high. When the load signal is low, it takes its inputs from these switches. All of these pins are pulled high. When the switches on the input pins are closed, the equivalent output pins are high. When the switches are open, the equivalent output pins are low. The output pins on the program counter match the data on the input pins when the load pin is low. Writing a CHUMP program is different from writing an Arduino program in that it has no IDE. Therefore, it can be written on basically anything. In this format, it uses a table with high level, machine level, CHUMP assembly level, and a comment. What you see in the high level column is meant to mimic what you would see in an Arduino IDE program. The address is the equivalent to the output signal from the program counter. The instruction is made up of 2 bytes. The most significant byte, or the leftmost bits, are used to define the instruction, and the rightmost bits or the least significant bytes are used to define a constant or a memory location. The CHUMP assembly level column translates what's written in the machine level instruction into something that we can comprehend, and the comment explains what the program does in further detail. Since all of CHUMP operates on 4 bits, the instructions can only have 16 lines. This also means there can only be 16 unique instructions and a range of constants between the values of 0 and 15 or -8 and 7, depending on how you read the binary values. What this program essentially mimics is a linear function. At the very start of the program, the value in the accumulator is 0. The program adds 2 to it, then stores the value now equal to 2 to the RAM address 7, which is labeled M, as the variable m in the equation y equals mx plus b. So the new value is 2, and it's stored to address m. Then the accumulator loads the value of 5 into the program and stores the new value of 5 into address x. Now the value of 5 is still in the accumulator. The program slowly will decrease the value of x as the value of y increases using the if 0 statement and the goto statement in line 1101 to create a while x is unequal to 0 loop. But it extends back to instruction 0011 to store the new value of x, saving the program some space. At the start of this while loop, the program reads the address labeled y, which is RAM address 2. It then loads the value. At this point, it is 0, and adds one value of m from its respective RAM address, stores the new value back to y. So m, at this point, is equal to 2. It's added to y. The new value in y is equal to 2. Then it loads the x address, reduces its value by 1, and goes back to instruction 3 to store it back to the address of x. It repeats this cycle until the x value or the x address value is reduced entirely to 0, by which point it can skip the while loop because now x is equal to 0 and go down to instruction 1110 and store the value of 0, which is still in the accumulator, to y. Then it loads 1 into the accumulator and starts the program back at the very top as the program counter increments from 1111 to 0000. With the new value of 1, the value of 2 is added to create a new value m, and then this will have a new effect on the y equals mx plus b equation. In the first run through, the y equals mx plus b equation brings us a y value of 10. In this new run through, it'll bring us a value of 15. Thanks for listening.